Alrighty. Okay, so as I was just saying to Ben, I've decided to call this building up a picture, the ubiquity of rendered targets in modern rendering. But it was kind of because I couldn't think of a better name for it that fits on a slide. If anyone remembers last year, Ed Blanche gave a talk about like an intro and a fairly deep dive into how a rendering pipeline works. And this is kind of a sequel to that, because if you understand all that stuff, that will get you an understanding of how rendering works as of quite a while ago, like 2003, kind of a while ago. So what I'm hoping to do here is to give a bird's eye view of what's happened since then. Not everything and not a deep dive, because there's definitely not time for that, but to give people a bit of an idea of like the overview of how things get done these days. So my plan is to do a really quick refresh of some of the stuff that Ed talked about last time. If you're watching this as a recording, I do recommend going and watching Ed's talk first. And that'll get us, as I say, to about 2003. And then I'm going to talk about what render targets are and what false color images are, which, spoiler, you probably already know, but we'll get to that. And how these things come together nowadays. So our really quick description of how these things work is we've got these things called draw calls and render passes. And how things basically work is you throw some geometry at the graphics card. It goes through this thing called a pipeline that includes going through the vertex shader, which decides, among other things, where the geometry is going to show up on the screen. It goes through the rasterizer, which converts a triangle in vector form into a bunch of pixels, although people in the know that that's not exactly true, but don't worry about that. That gets passed off to the pixel shader. The pixel shader decides the color that a given pixel is going to write to the screen, and then we write it to the screen. So these images of this diagram I've got here represents 3 draw calls, and it could represent a whole render pass. So if we've got a scene with these 3 shapes in it, we render those 3 shapes, and you can see the output of the render passes, this image we have on the right. First, it has a green square in it. Then we add a blue circle, so now it's got both. Then we add a red triangle, and now it's got all 3. Now, if we're doing this the traditional old school way, what we're doing is rendering to an image called a frame buffer or a color buffer that is what we're about to show to the player, what we're going to present to the player. So, you know, if you're making a game that runs at 60 frames per second, or at least that's the plan, you've got just shy of 17 milliseconds to come up with an image to put on the screen. And then you start again and come up with the image to put on the screen for the next frame. And the old school way of doing it is you pass geometry into the render pipeline and out it comes onto the screen. You do that with every object in the scene. There's your picture, and then we repeat. I'll just say really quickly that a certain chunk of cool new stuff that's happened over the last 20 years here belongs to the left of the pixel shader in this diagram that does things differently on the vertex shader stuff. That's not what I'm going to talk about today. But it is some interesting stuff. There's a lot more types of shader that come before the rasterizer nowadays that I'm not going to go into because, you know, finite minutes in the talk. Mostly I'm going to be talking about what exists on a kind of more high-level structural level outside of these draw calls. So first off, I'll also do a little bit of a revision of what a pixel shader is. So I have this weird context-free, this is like a character's shoulder from a screenshot I'm going to look at later, zoomed in very, very far. But a pixel shader is a special function, and a function for the non-programmers in the room is just a collection of code, a collection of logic, sometimes called a subroutine, that does a bunch of stuff to some inputs and creates an output. A shader is special because it runs on the graphics card, and a pixel shader outputs a color. So if we're drawing a picture, we're going to run an instance of this little pixel shader program for at least one for every pixel in our picture. So if you're running at 1080p, if you want to draw a frame, you've got to run a pixel shader at least 2 million times. Again, there's some little bits here where I'm like, I don't want to be too misleading. There's probably people in the room who are experts who are thinking, Finn's not completely telling the truth there. Some of these are simplifying examples, but broadly speaking, you run a pixel shader once for every pixel whose color you're deciding. And I have a little note here, by the way. Something that people have been eternally confused by is the difference between a pixel shader and a fragment shader, because you hear both terms. The answer is there's no difference and no one really cares. There's a pedantic difference between a fragment and a pixel that like rendering engineers need to care about. But broadly speaking, if I say fragment shader or pixel shader, I'm talking about the same thing. And that's always true. They're not two separate things. Fragment shader is the input. Sorry, a fragment is the input of the shader and a pixel is the output of the shader. So the naming's a little confusing, but don't worry about it too much. Now, it's also worth noting that if you have a function like a pixel shader, if it's the same function and it takes the same inputs, you'll tend to get the same output. Computers tend to be deterministic like that. So how do we vary the color of the pixels across a surface? We have different inputs for the different pixel shaders. And one of these is texture coordinates, right? Pixel shaders can make use of texture lookups. They have other kinds of input, but the crucial thing for the talk right now is a pixel shader makes use of textures as part of its input. So what is a texture? I kind of just feel obliged to have a slide with a name like what is a texture, but I'm not going to blow anyone's mind here. Texture's a picture, you already knew that. An image stored in VRAM is a slightly more pedantic way to describe it. And can be used for texture mapping if you carefully vary your UV lookups when you do your texture lookups. In this little example here, thank you Wikipedia for your free to use artwork on the texture mapping page. You can see this little map of a house, and then that's mapped onto a mesh of the house. So textures are usually created by an artist directly by firing up a paint program and painting the texture, or indirectly by, baking a high-res mesh onto a low-res mesh or some other process like that. So if that's a texture, what does a render pass create? Once again, we have this screenshot, I think, from one of the older Microsoft Flight Sim games. A render pass also creates an image, also an image in VRAM, in fact. And the traditional way of doing this was, as mentioned, we do a bunch of draw calls. We're rendering into an image, what we would call rendering to the screen. Essentially, we create this image that is the scene that we're going to show the player, and then we show them. So this little picture of a plane here, maybe we did a draw call to draw the plane. Maybe we did a draw call to draw the sea or the sky or the clouds. Once we've added those all together, we've got this little picture of a plane, and then we show it to the player as of about 20 years ago. But you'll notice this juxtaposition. A texture is an image stored in VRAM, and the output of a render pass is an image stored in VRAM. So what can we do with this? We can create a thing called off-screen rendering. That is to say, we're going to render to an image, and then we're going to use that image as a texture for more rendering. So a kind of slightly goofy example that I always use to talk about this is a security camera, right? Say you've got a game and you want to have a security camera in your game world, and you want that security camera to be streaming its feed onto a monitor in a control room or something. How would we do that? Well, you can't get an artist to draw the thing that's going to be on the screen, right? Because they don't know what's going to be on the screen. Maybe some character's going to walk in front of a security camera and we want to see that. So we do this thing sometimes called off-screen rendering. We're going to position our in-game camera to correspond to the security camera's position, and then we're going to render to a texture. The player won't see this texture yet. We're just going to render to it to show an image of what the camera sees. Once we've done that, we position our game camera back to where the player's camera is. You know, if it's a first-person shooter, then behind the character, the avatar's eyeball or whatever, and then we render the scene as normal. If it's the inside of an office or something, we're going to render the desk with the desk texture and the ground with the ground texture and the floors with the walls with the wall texture or whatever. But then when we render the monitor sitting on this that's streaming the stuff, we're going to render it with the texture we created from our security camera. And cool. So someone added this weird feature to graphics cards 20 years ago just so we could have security cameras in our game. But what if you don't have security cameras in your game? What are we doing with this? What use is a render target other than this particular contrived example? Turns out they're used for kind of literally everything all the time. And that's the big takeaway. That's what I'm talking about today. So let's say we want to do a post-process blur. First off, thank you to Harry Ridgway for this screenshot of a game he's working on at the moment. The screenshot on the left is the game. Everything else that I mess with here is just me messing with it. So we're making a first-person shooter, and I don't know, the player can get punched in the eyeball and then their screen gets blurry. We want to emulate the experience of getting punched in the eyeball very authentically here. So how do we do that? How do we blur things? What we're going to do is we're going to render the scene crisply as normal to a render target. So this image you've got on the left here, the crisp one, we're going to render that first to an off-screen buffer. The player doesn't see it. Then we're going to render again to the screen using that texture we just created. And this brings in a slightly little confusing fact here, because when we're creating this image on the left, how many draw calls are there? What are we actually doing? It's like, well, we've got to draw this gun. We've got to draw the ground. We're going to draw the walls and these particle effects here and the muzzle flash from the gun firing and whatever. We're rendering the whole scene. So what are we rendering on the right? We're rendering 4 vertices. That's it. We're rendering one thing called a full screen quad. It just happens, it's a quad that we elaborately cause to render right in front of the camera so that it takes up the entire view. So a somewhat odd fact of modern gaming is, in a sort of stupid pedantic way that doesn't really matter, most of the time when you look at a modern game, what you're looking at is one quad that's rendered in front of the camera. It just happens to have a very elaborate texture that looks like a video of the game playing. In this case, when we render it making use of our color texture. So sometimes you'd call that the screen color, the scene color. We render it on the right with a special shader that blurs it, right? So it's worth noting, like, a lot of the techniques I'm going to describe here as being possible thanks to render targets, rendering to a texture, is the result, are techniques that depend on things that cross the boundary between two triangles, if that makes sense. As in, you can, if you're drawing a triangle, sure, you can blur the texture on the triangle in a pixel shader, but you can't blur the silhouette of the triangle as you draw it. That's not something the pixel shader has access to. But once you've drawn it to an image, you can then blur the image. And it's a pretty good hint if you're trying to do something like that that spans two triangles, two different pieces of geometry, then good odds rendering in multiple passes to a texture like this is something you're going to want to try. So, okay, I'm just going to switch gears for a minute and talk about false color images. Bit of a caveat, I haven't actually, a false color image is an image that where the pixels represent something other than a color that a human actually would look at. I'm not sure that I've actually heard this used, false color images, heard this used in a game dev context. It's usually, cool astronomer photos, a picture of the Eagle Nebula or something that's a false color image. But whatever, I'm going with it. It's a false color image. Now, there's a bit of a recurring theme last year and today as well on Technically Games, which is enlightenment can be achieved by understanding that data can be whatever you want it to be. I think Shane's talk this afternoon is pretty much about exactly that. Data is whatever you want it to be. And that's very true with false color images, right? So from left to right, I've got this little elephant here that was some of the example art for some software I released a few years ago. We've got the diffuse map on the left. It's not really a false color image, that's gray means gray. Second one across, though, you'll probably recognize as a normal map. Very common form of false color image. The red, green, and blue aren't red, green, and blue. They are here because we're visualizing it, but what it really means is the X, Y, and Z components of a vector that has to be used to interpret the orientation of a surface. So you can see the bits of the elephant that sort of start to look a bit pink have a higher red component because the surface is facing to the right. The X component is getting high, and X is represented by red. Likewise, the green component represents Y. So the back of the elephant, where the surface is facing upward, starts to tilt a little bit green. I kind of was just giving examples, so don't have to talk in depth about what all of these are, but the next one along is a depth map, and the one after that is an anisotropy map for rendering anisotropic highlights like grooved surfaces and stuff like that. So why did I just take that funny left turn from talking about render targets to talking about false color images? What do they have to do with each other? Now, this is really key because as soon as you understand that a pixel shader can write to a false color texture, you can start to sort of transform the way you think of these things into understanding that a pixel shader and a render pass is just a way of populating an arbitrary array of data values. And maybe they can be colors. Eventually they're going to be colors, probably because we want to show them to the player. But in the intermediate steps, we're just populating arrays of data that we can use later. And we can visualize them because that helps with debugging. It's very hard to look at, 2 million 2 million numbers per frame and understand what the hell's going on. So you tend to visualize them like these visualizations here. But we're just going to be using a render pass to position some geometry into an array. And what that array means is up to us. We're going to do a render pass. It's going to create this data. And then a subsequent render pass is going to use this data. And we're going to do this over and over and build up until right at the end, we've got our final image that's actually in color, real color, and then the player can see it. It's a little bit like, although it's not a perfect analogy, but artists who have used layered art tools like Photoshop, individual layers are not what the final image is. They're just building blocks. Each of these render targets, just building blocks. So instead of blurring the whole screen, because that's, I don't know, probably not a very good game feature, let's say we want to blur certain parts of the screen. Maybe you've got super hot objects in your game and they have like a heat haze, or splashes of water can get on the camera, like get in the player's face, and we want to distort that. How would we do that, right? We're not just going to distort the whole screen. Back here, we were blurring the whole screen. But how do we tell our shader which parts of the screen to blur? What we need is a distortion image. This funny, kind of ugly looking thing here in the top right. So what is that? It's the red-green channels represent the horizontal and vertical distortion that we're going to apply. So kind of this crappy middle yellow color is going to be 0.5, 0.50 or 127, 127.0. That represents the middle of the range of numbers that we're representing, i.e. no distortion. When the color gets a bit different, then we do something a bit different, right? So the images here, the top left, it's the first render pass. We do the geometry exactly as we did with the blur. We render the whole scene, the gun, the walls, the floor, particles, etc., into our scene color. Then we start rendering to a different image. We're rendering to our distortion map. What are we rendering now? Probably just a couple of quads. We're probably just going to render like some particles with a special shader where blobs of water have hit the player or whatever, or where a particle system represents fire and is distorting. You want to have a heat haze effect or whatever. And then we make use of textures 1 and 2 to render our full screen quad. And I'm not sure how well this is actually coming through. I made this image as big as I could without the rest of the slide becoming compositionally incoherent, but I don't know how well the stream will pick it up. But hopefully it's visible that these these particles on the left and then up on the top right and then to the right of the gun are kind of distorted and messed with in a way that corresponds to image number 2. So in this case, how many render passes are we doing per frame? 3. We're rendering our scene color, we're rendering our distortion map, and then we're using both of those to render the final image. So little bit of a distraction here. Let's talk about a special kind of false color image called a depth map. Now, probably people are familiar with the concept of depth mapping, sometimes called depth buffering or Z buffering, or Z buffering, I suppose. Very old technique. It actually, funnily enough, given that it's a false color image and all those things that we've been talking about, it predates all this render target shenanigans that I've been talking about. In fact, it predates programmable shaders entirely. As far as I'm aware, the earliest thing, like the first console with depth buffering in hardware, was the N64. So this goes back a long way. And so this, once again, courtesy of Wikipedia, we have this little picture of our sphere and our cube and our Blender monkey head example. Top left is the scene color. Bottom right is the scene depth, where the higher the luminosity on every pixel, i.e. the whiter it is, the further away it is. So the closer up objects are darker, the distant objects are further away. And almost any time you render a scene in 3D, you're going to be using a depth buffer because it's used by the pipeline for, what's it called? Occluding individual pixels for depth independent drawing. I'm not going to go into too much detail there. Just once again, Ed's talk is a fantastic reference. I'm pretty sure he talks about depth testing there. But for our purposes, it's very interesting because that's just another array of arbitrary data about the scene, and we can use that in subsequent passes. So you might be thinking about that little bottom right-hand corner photo image. It looks kind of like a really dense fog has descended, and that's how fogging is done. But there's other stuff we can do. We can use that for depth of field. We can strategically blur things based on how far away they are from the camera. We can also do atmospheric attenuation, which is pretty similar to fog, but that thing where, you know, a mountaintop on a clear day might be the right color, but on a slightly not clear day, it tends to tilt bluish in the distance. We can also use depth maps for another very interesting and quite old technique. What if we were to render a depth map from the point of view of a light source? Suddenly we have a grid of data that represents how far the nearest opaque object is from a light source in a bunch of different directions. Turns out that information is exactly what we need to decide whether any given point is in shadow. This is called shadow mapping. What that means is if you've got a dynamic light source that casts real-time shadows in a game, mostly, I think it's probably fair to say almost always these days, that light source gets a render pass all of its own just to create a shadow map so you can tell what's illuminated and what's occluded. Again, there's this theme of these techniques are great when you've got a lighting effect that exists between triangles. One triangle is casting a shadow on another triangle, so you can't easily do that just in a pixel shader. It takes another render pass. So the last thing I'm going to talk about before we get into specific examples of how this all works is multiple render targets. Again, a technique that's been around, or I shouldn't say a technique, a hardware feature that's been around for a while now. I mentioned earlier that the output of a pixel shader is a color, and that's a little bit of a lie. It can be a color, but it can be several colors in a single draw call. This is a really common thing when if you might have heard of deferred rendering, and that's what these examples here are, where you're a single pipeline. You'll throw, here we have a plane, a torus, a sphere, a cone, and a cube. We're going to render those once. They go through the pipeline. Vertex shader executes once. The rasterizer executes once. I mean, per thing. The pixel shader executes once as well, but you're going to have a special pixel shader. It doesn't just output one color. It outputs three. It outputs the diffuse color on the left, the depth, it's inverse depth for some reason, and the normal on the right. And those three images, suddenly we have a bunch of information about all the objects in our scene conveniently arranged in this grid, where we can say, okay, at any given point in the scene, where is that pixel? What color is it? It's albedo or whatever you want to call it. And the surface orientation. And we use that information to calculate the lighting later, hence deferred shading. So there's a couple of techniques that we've had for a little while now. Now I'm going to talk about some particular examples. These examples are all drawn from random projects of mine, not because my projects are particularly interesting, but because I have unambiguous access and rights to publish imagery from them. So this is a game jam game I'm working on at the moment called Snake Hill Downhill. And say we want to render some text that looks kind of like 70s, this look I've got going on here. How would we do this? So the easy answer is, ask an artist nicely to make this image for us and then just draw it on the screen. And, nothing wrong with that especially, but it does have some downsides. It means you need a different image for every piece of text you want to render with this technique. It means you've got to get the artist to redo it if you have your game translated into different languages. Or if you switch fonts, you've got to regenerate everything. So that kind of sucks. It'd be cool if we can just render this ourselves dynamically. But how would we do this? Because when you look at this text, you see, oh, well, we can't really just do it with a bitmapped font, right? Because, the S and the N have to interact with each other in a certain way. There's no image that I can create for the S that I can just blend with the N to get that look. And again, there's this theme of it's very hard to do things that involve overlap between two pieces of geometry like that. So to solve this problem, we're going to talk about a thing called a signed distance field. Signed distance fields are really cool. So they were sort of popularized by Valve. I think they published a paper about using signed distance field font rendering in around the days of Team Fortress 2. And they are usually used for rendering glyphs. If that's a weird term, I mean, that is a pretty weird term. Glyph, usually in the context of font rendering, just means a character, but it's a better term than letter because it doesn't imply, it might be a number or a piece of punctuation. It might be from a language that doesn't use the Roman alphabet. And the term character implies it's 8-bit in certain contexts, which wide characters aren't. So anyway, glyphs. Signed distance fields are often used for rendering glyphs. Now, here I have a picture of a signed distance field for the letter X. What's going on there? Well, the color of the pixel represents, if it's darker than middle gray, the fact that it's outside the glyph and how close we are to the nearest part of the glyph. So you can see that as we get further and further from the edge of the glyph, we get darker and darker and approach black. If we're brighter than middle gray, then it represents how far inside the glyph we are. So a very simple font rendering scheme involving sign distance fields would be a shader that just looks up the sign distance field value and says, oh, check if it's greater than 0.5. If it is, render the color of the text. If it's not, throw that pixel away or render it black or background color or whatever. But what if we render this into a special off-screen buffer, right? Now, if you look closely at this, you can perhaps convince yourself that every point in this grid of data represents how close we are to the nearest glyph. For people in the know, this is a rare use of the min blend mode, which is a bit obscure and it's sometimes hard to guess why it's even there. But this is rendering with that funny blend mode to get us this funny looking image that, not to belabor the point, the player will never see. This is rendered off screen. Then we combine it with another funny looking image there in a shader to get us the effect we want. It's actually a very simple shader, right? If you look at this, I've blown it up so that it's actually visible in the slides, but that image in the top right there is a 256 by 1 pixel image, a one-dimensional image essentially. And in the pixel shader, we get the gray level from our sign distance field image, and then we use that gray level to figure out where in this texture we're going to get our color from. So remember I said higher than 0.5 means we're inside the glyph. If we are to the right of this strip texture, we get this brown color, which is inside the glyph. To the left of it, as we get further away from the nearest glyph, we cycle through these colors, and the end result is this sort of 70s look we see below. So we're rendering our font over a couple of render targets. So next example I'm going to talk about is from the other game I'm gradually chipping away at. You may recognize this because this is the game with our little bipedal animation stuff from the talk I gave last year. So it's called Sunshine. And I tried to come up with this scene here where a fair bit of stuff is going on. And so I can take us through how this scene is actually constructed. So what are we looking at here? There's approximately 2 things about this scene that are of any technological interest. From a rendering point of view, we've got the lighting. There's a bit of global illumination going on. You can see this cave here has this sort of spear of sunlight coming through, illuminating the ground down below. And we've also got this little lamp burning over to the left in the cave, illuminating some stuff around it. But also the dark parts are not completely dark, except the parts that are actually inside the earth. And the other thing is the kind of soft, mossy, fuzzy stuff covering the ground. It's probably not immediately obvious what that is. Is that geometry? Like from a tech point of view, is it geometry? Is it sprites, a particle system? What's going on there? So I'm sure it'll come as no surprise that, of course, the first thing we render is this thing. Okay, what is this thing? What is an occlusion buffer? Well, crucially, probably occlusion buffer means a specific thing to someone, but it's a term I made up because programmers do what they want. An occlusion buffer is just a grid of pixels that represent something that I need represented for my weird custom shenanigans, right? So broadly speaking, each pixel here, if it's white, it represents light cannot pass through that pixel in the foreground or the background. If it's cyan, it means light can't pass through that pixel in the background. And if it's yellow, it means light can't pass through that pixel in the foreground. A couple of other things to note here. One is this isn't even the same scene, right? Or maybe it is, but we've got to look a little bit closely. If you look at that little aperture of the, I don't think my cursor is actually visible in the stream, so I'm just going to assume it isn't, and I mean, it shouldn't be, or else it's been annoying you this whole time. So I can't really gesture at particular bits, but if you look at the shape of that cave, you can see here that that shape of that cave is in this image, just in the middle, right? So this occlusion buffer shows a much larger view of the world than this scene here. that much larger view of the world is because we need the lighting system to exist outside what's visible. Otherwise, we end up with light sources winking out of existence the moment they're not on, like in shot, which is not what we want. So we create this funny thing. Why? Because of the next step. Now, I'm not going to go into the weird magic of this lighting system because it's too weird. And I was actually almost going to give today's talk about this lighting system. Maybe that I'll save that for next year, perhaps. But we have a bunch of these lighting buffers that represent weird internal data to do with the ambient occlusion. Sorry, not the ambient occlusion. What am I trying to say? The global illumination system that we've got going on here. But if you look at the top left and top right images here, they're just a sample. There's more images going on, but they represent that little hotspot there is the amount of light coming from that candle going southwest and northeast-ish. And then the bottom image represents the sunlight in the foreground and the background, and you can clearly make out that shaft of light going through there, right? So one thing I will note here is that these images in Sunshine are much lower resolution than any images are in, like this scene was rendered at 1080p. This occlusion buffer, I think, is about 1080p. I forget, but it's reasonably high res. These lighting images are like, I think 240 by 144 pixels or something ridiculously low res like that you'd think you wouldn't be able to get away with in any modern context. But, you know, you save time where you can. It's much quicker to render these images at low resolution than high resolution, as anyone who's ever tweaked the graphics settings on a PC game knows. High resolution costs more. Okay, so once we've done that, what do we do next? Hey, look at that. We have an actual image that kind of resembles our final scene. I made a little note here. Why is the scene so dark? Ask Ryan. I guess what I mean is, for those who attended Ryan's talk this morning, this scene is very dark because it hasn't been transformed into the color space that we want to use yet. There's a few other funny things going on. The scene is lit. We can see that shaft of light, and we can see the hotspot behind the candle, and we can see the player and the furniture, but we can't see the moss yet, right? I don't know how well this is coming through on the stream because it's a pretty dark image and maybe the compression is annihilating the quality. I'm not sure, but the surface of the earth here is bare. There's no moss. It's very clear on the background layer against the sky. There's no moss here yet. Speaking of moss, here's our moss buffer. This is rendered with particles. You can see there's blobs of green on all the mossy surfaces. You can also see that these last two images, if I flip between them, represent the same camera view of the scene, and it's the scene that we're going to finally end up with. But that's not quite enough. We've also got moss normals, because we need the moss to be illuminated. If I flip back a few frames, you can see the moss is getting, it's not terribly obvious in this under these lighting conditions, but the moss is illuminated. So we render moss color and we render moss normals. This is actually done with multiple render targets, as I mentioned. These two images are created with a single pass, so we don't have to transform our all these little moss particles twice. It's the same resolution, as in its screen resolution, 1080p. It's the same camera. And then, just as a little side note, this moss looks crap, right? Look at that with this little zoom in. It's sort of these crap little circles, and the normal map is this really crummy, hard-edged sphere sprite thing that doesn't intersect properly. Why would I do this? And why does it not look like that in the final pass? Because, again, it's that whole thing. The render targets are great for when you've got different pieces of geometry that have to visually interact with each other. What we're doing is we've got these two images, and then we're going to blur them to soften the final effect, and then use the blurred normal values and diffuse for the lighting. And so that's why we get this kind of this soft, fuzzy outcome. So we go from these, and then we draw our moss as well as some transparency, although there's not much of that in this screenshot. Now we've got moss in our scene. Cool. The light's still looking pretty broken. That's where gamma and tone mapping comes in. Now, again, I refer you all to Ryan's talk this morning. Gamma and tone mapping is, gamma is like, you know, when you play a horror game or something and the first thing it says is slide this slider, and there's like 3 pictures of the studio logo or something, and it says adjust this until the one on the left is barely visible and the one on the right is visible or whatever. That's you doing your gamma adjustment, because different screens and different lighting conditions need different gamma settings. So from there to there, we're fixing up gamma, and we also do a bit of tone mapping to sort of set the mood depending on the time of day and how far underground you are and that kind of thing. Okay, are we done? Not quite. But I will just point out, for all these passes, what geometry are we rendering? Here, we're rendering tiles or anything that casts a shadow. Here, we're rendering full screen quads. Just not much geometry, single draw call. Once again, here, we're rendering actual geometry. Each of these blobs of tiles and the furniture and stuff, we're rendering that geometry. Here, we're rendering a bunch of little particles. Same for that. Now, we're rendering a full screen quad. That moss is done as a full screen quad at this point. It's more like compositing 2 images together in Photoshop. Once again, this is another full screen quad where we're fixing up our lighting. And finally, we bring in our UI. We do the UI last because we don't want it to get tangled up in the tone mapping. Turns out UI artists don't like it very much when their finely selected colors get screwed around because the time of day changes. Speaking of UI artists, this is all placeholder. Don't blame them. So now we are rendering finally to the screen. This is what the player is going to see. Now, that's not everything we're going to do for Sunshine. We're going to have fluid, like water rendering. That's going to go into its own render target. Rainfall is going to be done on the GPU in a separate target. Particles will probably be different, and distortion mapping, very closely resembling what I talked about in that example earlier. So this seems like a lot of stuff, right? Like, this is this sort of simple-ish indie game. We're doing... I hand-waved a few things here because I didn't want to get too far into the weeds with the implementation details, but we're doing between 12 and 20 render passes, all fitting in that 16 millisecond window just to create a single frame for the viewer to see, and then we're doing it all again. And that seems kind of ludicrous if you haven't really gotten your eye in on this way of doing a render. But this 1080p screen was rendered on my kind of crappy little Surface Pro on integrated graphics, and it hits 60 FPS just fine. Modern graphics cards are really, really shockingly fast, even slow ones. Also, Sunshine is really not very complex compared to modern games. I did a bit of hand waving, but as I say, it's a dozen bit more render passes. A single frame in Doom 2016 involves around 50 render passes, and 2016 was 5 years ago now. The main purpose of me giving this talk is so we can get people this idea that, like, I think the link in the talk was called Render Target Freestyle. We're really just mixing and matching a lot of render passes, and that's just what modern rendering is these days. So we're not stuck in 2003 anymore, but it's a stretch to call this modern rendering exactly. These are techniques that have been possible on the Xbox 360. The Xbox 360 and the PS3 were the first console generation where this stuff was really the norm. I mean, you couldn't render Doom 2016 on the Xbox 360, but multiple render targets were in. Stuff like distortion mapping was in. All this stuff has been in hardware for a good long while now, but it is how modern rendering is done. I made a vague gesture towards, like, you know, you might be thinking, yeah, but what about the magic weirdness that Unreal 5 has going on and Nanite? And what about really modern rendering? What's the new hotness? Most of that stuff, to my knowledge, takes place to the left of the rasterizer, as in prior to the pixel shader. So these techniques that I'm describing here are not the complete picture for absolutely cutting edge rendering techniques, but they're a part of the picture that's still very much relevant and not, as far as I can tell, all that commonly understood. So where do we go from here? A lot of people's understanding from this can come from graphics studies. So a guy called Adrian Courrèges, I'm like 60% sure I'm pronouncing that right, does really fantastic graphics studies of popular games. And one particular popular one was the Doom 2016 graphics study, where he'll go into a lot of detail of all the things that make up a frame. There's also a fantastic graphics studies compilation. It actually goes back far enough in history that it predates a lot of these techniques. There's like the earliest one on there is Shadow of the Colossus, I think. But there's also a study of games like Red Dead Redemption 2, The Witcher 3, lots of stuff like that. Also The Witness, which I found very interesting because The Witness is a rare example of a small indie game, well, a small team, I suppose a pretty large indie game, all things considered, that does its own thing and is quite stylized, and its pipeline is very focused on the style that it was trying to achieve. So it's really cool to sort of do a deep dive as to how those things are doable. So if you want to have a look at that, if you want to take it to the next level, there is this wonderful program called RenderDoc. It's ostensibly for debugging and examining the graphics of your own games, but you can use it for other people's too. You can download RenderDoc. It's not the easiest program to get into if you're not technically inclined. It's not trivial to potter around with and look at things, but it's really cool being able to look at your favorite game and see what it's doing, if it's doing something a bit weird or interesting. I'll just really quickly say, if you've used an engine like Unity and you've had to choose, like, do I use Universal Render Pipeline or HD Render Pipeline, that kind of stuff, the difference between those different pipelines is all this kind of stuff. What targets get rendered in the meantime, what depends on what is going to be different between those different pipelines. I think that's about it, and I think I have approximately 90 seconds for questions or something like that. But yeah, that's it from me.
Thank you, Finn. You actually got some good timing. I'm very impressed.
Thank you.
This is fascinating. I love this stuff. It's stuff that doesn't really get taught, especially with modern engines. When you get thrown to Unity and just like, which target do you choose? Oh, this one. This one looks better. I have no idea what happens or how any of this works in the background. Why isn't the shader drawing in the right order? And it's just this basic knowledge is really all missing, obfuscated a lot.
It's what this conference is for, right?
Yeah, and I love hearing this type of stuff. There's a couple of questions. We've got one about split screen multiplayer. Is it usually done with render targets?
I think these days it would be, yeah. So yeah, you would essentially be doing probably, you wouldn't want to do like have a post-process blur or something that causes the blur to like go across the boundary in the middle of the screen or something. So I think you would essentially just render the whole lot 4 times or whatever, and then in a final pass place those 4 textures. So yeah, exactly that. Back in the day, it would have been done slightly differently using something called a stencil buffer probably, and just only render to one half of the screen and then only render to the other half of the screen. But nowadays, that's how they would do it.
Awesome. Is there any technologies on the horizon that you're excited about that's coming into video cards that make you happy?
I mean, honestly, it's funny because the last time, say, the OpenGL standard was updated based on a hardware shift prior to the Turing graphics cards, as in the GTX 2000 series and ray tracing and all those shenanigans, was like the GTX 600. Like, you've got to go way back before there's actually hardware changes. Honestly, I think the newer stuff with ray tracing and all that, the coolest thing is actually not the ray tracing. There's a lot of these nifty techniques, like there's something that allows you to render in different levels of detail on different parts of the screen, and I can't remember what it's called, but it's very useful for optimizing like a virtual reality game where you can render super high detail right where the player's eyeball is looking, right on the fovea, and then everywhere else we don't care because VR headsets have a lot of pixels and a very demanding frame rate. And that's going to be a huge win for performance, allowing you to do that kind of stuff. There's a lot of kind of nifty stuff that snuck in when ray tracing became common that no one talked about because ray tracing is shiny.
Everyone likes the ray tracing, but
But yeah,
no one's using it, but but the amount of power that comes along with it, I think everyone is excited. Development side of it, I see everyone's like, "Oh, this I can do all this calculations." Someone was talking about using it for sound bouncing, using that for calculating what sound is in the scene, and that's amazing.
Yeah, well, there's one of the things that comes before the rasterizer that I sort of hand waved at the start of the talk is a thing called a compute shader that's actually been with us for ages, but a thing called a mesh shader that essentially, instead of passing geometry in as a mesh, we get to just run arbitrary computations to decide what goes into the rasterizer, which I don't have a complete knowledge of the deep dive of how Unreal 5 works, but I strongly suspect a lot of the weird magic of high, like millions of polys per thing, is cleverness by replacing the vertex shader part of the pipeline with basically arbitrary compute shaders. And so that stuff's going to be really cool. Yeah, maybe that's another talk.
So many talks here. If I listened to what you just said and said, this is awesome, and I want to actually learn how to write shaders or understand the process or make my own pipelines, where do I go?
If you're a programmer and of a adventurous sort, one thing you can do is do some OpenGL tutorials and build it from the ground up. If you don't want to do that, you may have come across the term a scriptable pipeline in Unity, of which the HDRP and URP are both examples. And that's why those download as assets, right? You can actually go in and look at the script that goes, oh, now I'm going to render this, now I'm going to render this, or whatever. And you can, I believe, I'm not a Unity expert, I believe you can write your own scriptable render pipeline where you have very direct control over these things. And so that's not a bad place to mess around with that stuff.
Cool. I just want to see if there's any more questions in the chat. Everyone is more just like, wow, this is so freaking awesome. This is great. Which I totally agree with. I've always always heard all this stuff referred to as black magic, especially if you're a programmer, because if you type things wrong, it just doesn't work. At least with, it's just like, hey, here's magenta. Congratulations, you've broken everything.
The color of failure.
Which always annoys me when people put magenta textures in their games, because it just screams you've broken something. And all these retro games coming out with magenta grids in the background are just like a scary.
Magenta has been the universally hated color since way back in the day when we didn't have enough memory for a proper alpha channel, and so perfect magenta was used as a stand-in for transparent. Because everyone, since the late 80s, people have said, no one really wants to see this color. We can use it for something else safely.
Are you going to make these slides available to people?
Sure. Don't see why not.
Yep.
I'm happy to do that. It's
asking about it. But if you'll be around the chat, I'm assuming. So please go
sure thing.
Hassle Finn, and he will answer. He will happily answer any shader questions you have. But thank you so much for being with us 2 years in a row.
Not at all. It's been a pleasure.